Good afternoon all. So in this particular lecture, we will be discussing some of the statistical features, right? So in last semester, we studied a course numerical and statistical method. In that, unit number 5 was related to statistics. And we saw different uh, features or measures of statistics, and by using those parameters we were trying to analyze the data and make some prediction. So in this particular lecture we will be reviewing those fundamentals, and that we will be taking here as a feature. So just the word changes there, that is feature, otherwise it is actually a statistical parameters. So we will initially start with the measure of central tendency. In that, we need to talk about mean, mode, and median. So when we say mean, means it is the simply the arithmetic average of the data points. Okay, and it is denoted by a symbol mu. So suppose you have 6 subjects and you got different marks in those 6 subjects. So what you do, you just simply take average of those marks, right? And that will be considered as a mean, and you say this my percentage is 70%. So this is the simple example of arithmetic mean. But every time we cannot rely on mean. Why? For example, suppose student A is there and student B is there, and in mathematics A student received 90 marks out of 100 and B student received 40 marks. And similarly in biology subject, A student received 40 marks and B student received 90 marks. So if you take average percentage of student A and student B, then it will be same, right? But we cannot treat both student A and B equally, because from numbers A is good in mathematics whereas B is strong in biology. And therefore, even though their average is the same, that is mean value is same, but we can recommend student A to go for engineering and we can recommend student B for biology, that is medical field. So every time we cannot rely on the value of mean. So that's why the feature is mean. From the data we extracted feature mean, but is it a really useful feature? That is important question, and that we need to decide. So this is the two sides of the feature mean. That is, sometimes it is a very good tool to find out the performance of the student. For example, university rankings are based on their marks, percentage marks they received in the given academic year. So there is a good indicator. But when question comes related to in which program or field I should do a career, then what I will do, I will not check mean marks. I will check how is my performance in the mathematics. Based on that, I may decide to go for engineering. And if my performance in biology is very good, then I will go for medical field. So this is how we need to take the decisions. Again, the second question related to mean is, suppose two numbers are there, 4 and 6. Its average would be 5, right? And again, there are two more numbers, 2 and 8. So its average is also 5. So can we treat them equally? No, we cannot treat them even the average is same, because if we look at the spread of these two number and if you look at the spread of these two number, then it is not comparable. So therefore in this case also we cannot rely on mean value. And therefore one more term come into the picture, that is median. And median is the middle value when the data is data set is arranged in ascending order. So suppose 0, 1, 2, if you arrange up to 100, then in this case the middle value would be 50, right? And that can be considered as a median of the data. So sometime we need to rely on the median values as well. Again, mode. So sometime mean is also not useful, median is also not useful. So in that case, we rely more on the mode. So mode is defined to be the value that occurs with the greatest frequency. Okay, and in order to understand mean, median, and mode, let's take one distribution. Okay, so let's say this is x-axis, this is y-axis, and the data distribution is shown. You can see the distribution. So inside this, there are all data points are there inside this area. So this particular graph represents how the data is distributed over the plane, right? And if we take average value of all the data point, then it will come here. You can see this vertical straight line, which is called as mean. And mean is nothing but the average of all the data points. Now, when we say median, then this is the lower limit, right? Let's say x naught. And this is the highest point, let's say xn. Then this is the median in this case. So when the data points are arranged in ascending order, then it is the middle value. Again, mode is nothing but the value that occurs with the greatest frequency. So when you look at this distribution, then at this particular point or in this region, maximum data points are concentrated. So that's why this particular point is called as a mode. Okay, and especially when the data is skewed, in this case it is skewed data, right? It is not normal distribution, right? In this case the concentration of data is in this direction. So in this case it is good idea to rely more on mode if we compare with mean value. So such type of decision needs to be taken. So when we talk about central tendency of the data, there are three features: mean, mode, and median. So in statistic, we were calling it as a measures of central tendency. But here in AIML, instead of word measure, I am saying a feature. So there is just difference between the words. Otherwise, meaning is as it is. Okay, so we saw the mean, mode, median. But again, about mean, you can see how the data is spread in both the direction. And it is very widespread data, right? So that we need to measure. And that is called as measures of dispersion. And when we talk about measures of dispersion, then different terminologies come into the picture. So first one is range. So it is the difference between the maximum and minimum value in the data. Suppose a data set is there, and in that data set the minimum value is 0 and the maximum value is 110. So if we take the difference between these two values, then it is called as a range. So mathematics point of view, we can very easily understand, and whatever answer would be there, if that number is big, then we can say that the data is very spread. But suppose in other case the minimum value is 5 and maximum value is 10, so we can say that spread is less. So again, that depends on the context and what type of data you are analyzing, right? So range is useful to measure the how data is spread. Again, the second parameter come into the picture, that is variance. It is defined as the arithmetic mean of squared deviations of a given data set of observations from the arithmetic mean. So we calculate the mean. Then from each and every data point, because we have n number of data points, so from each data point we subtract the mean value, then we take its square, and then we take its average. So it is called as variance. So this variance again talks about the distribution of the data. So this is the extreme point and this is another extreme point of the distribution. So again, in order to quantify this spread of the data, variance can also be used, and this is a particular typical formula that is used. Again, if we take the square root of variance, then it is called as standard deviation, and this is the formula for standard deviation. So this is the mean of the distribution, and for that data, if we estimate the standard deviation, then we can put plus sigma here. Again, we can put at other side, that is minus sigma. So we may think that for this particular standard deviation, how much population part is there? We may be interested to know. Again, if we go ahead, then it would be 2 sigma here. Here it would be minus 2 sigma. And we may be interested to know how many data points are lying within this 4 sigma. And again, we can go ahead and we can say that this is plus 3 sigma, it is minus 3 sigma. So this concept of 6 sigma came into the picture. So what I wanted to convey here is that we cannot rely only on the mean, mode, median, because they talk about only the center point of the data. But in a real practice, we need to consider the variation. And we will take a typical example for this, right? So suppose you are designing a gear, and in that gear you are expecting the diameter, the pitch circle diameter of the gear should be 80 mm, let's say. So as per your design, you are saying that pitch circle diameter of the gear should be 80 mm, and such 1000 gears you want to manufacture. So practically, when you start manufacturing that gear on a machine, then all the gears will not be manufactured with 80 millimeter diameter. 80 millimeter diameter is a design requirement, but due to machine limitations, every time you will not get the same, right? You may get 80.01 mm, 79.88 millimeter, and so on. All the values will be close to 80, but exactly 80, very difficult. And if you plot those data points and look at it as a distribution, then you may see a distribution like this, not exactly like this, but similar distribution you will see. And for that distribution, what you will do, you will find out mean value. And suppose the mean is observed to be 79 point, let's say 95. So 80 mm was design requirement, and from machine you got 79.95 as mean value. So there is a deviation between your expected value and actual value. So again, in this case, we as a design engineer know that machine will not perform in a similar way over the period of time. And that's why it couldn't manufacture all the gears with 80 millimeter diameter, and that's why this deviation is there. So generally what engineer do, it will say we are expecting 80 millimeter, but with some tolerances, let's say point sorry, some tolerances, let's say sorry, 0.01 millimeter or sorry. Okay, so designer, what designer will do, he will put some tolerances. 80 is our design requirement, but plus minus 0.05 is acceptable. So this is the design tolerances, and your machine manufactured some components, the gears with the diameter, mean diameter of 79 point, let's say 95. Okay. Again, this is the mean value 79.95. Again, both side there will be a spread. So all the gears having diameters between the upper limit and lower limit defined by the designer will be considered as accepted components, and remaining will be the rejection. So this is how whatever standard deviation is there, it is an input for designing the tolerances, and based on that you can decide the criteria for acceptance and rejection. Again, we will take other case. Suppose that gear is to be used in very critical application, let's say wristwatch, which shows time, so there should not be any kind of deviation. So in that case your tolerances would be very tight. So it is acceptable, but plus minus, let's say 0.0001. So here when you look at the tolerances, it is very tight, and therefore if you know there are three machines, let's say A, B and C machines, and from the past record of these three machines, if you observe that the C machine is very precise and it can accurately manufacture the component as per the requirement, then you will manufacture that gear on C only. So here we have utilized the past data of machine A, B and C, and based on that data analysis we decided which machine is to be used for manufacturing such tightly designed component. So both way you can use the standard deviation. Okay, then we will go ahead. So from these two slides, what we understood, that we every time we cannot rely on mean, mode, median. Along with that, we should think about range, variance and standard deviation. Again, one more term come into the picture, which is called as standard error. The sample mean may change from sample to sample. The extent of variation in these sample means is measured by quantity called as standard error, and this is the typical formula for the same. So why this is very important? Suppose machine A is same and that machine has to manufacture a component at 80 millimeter diameter. Okay, now on that machine runs in 3 shifts: first shift, second shift and third shift, right? And each shift it will run for 8 hours. And again assume that for each shift the operator is different. So thing is that in first shift the performance of the worker will be different, performance of the machine will be different. Again, during that 8-hour span, some wear tear may take place, and that has to be taken care by the worker. So again in shift 2, the performance of the worker, performance of the machine also differs. Again in shift 3, the performance of the worker and machine will be different. So these are the variations. So let's say 100 components are manufactured in shift A. So for those component, the mean, let's say mu1. Again in shift 2, 100 components are manufactured, and let's say their mean is mu2. And in third shift again 100 components manufactured, and let's say their mean is mu3. And it will have some standard deviation as well, sigma 1, sigma 2, sigma 3. So theoretically, if we think about three shifts, so this mu1, mu2 and mu3 must be same, and sigma 1, sigma 2, sigma 3 must be same. Why it will be same? It should be same because machine is same. But practically it is not possible because over the time the machine degrades. The tool behavior changes, tool worn out. The worker will not take proper precaution while carrying out the operations. And because of this all uncertain parameters, for each shift you will get different mean and standard deviation. Now the question comes that can we accept all the three lots, or the quality of components manufactured in first shift, second shift and third shift are the same? So in order to verify that, we rely on standard error. So we take the ratio of sigma upon square root of n. So in all the three cases, the sample is 100, 100, 100. So square root of n is 100. N will be 100. But sigma will change for all the three samples. And when we take the ratio, and if it is observed that the standard error is nearly same for all the three samples, all the three shifts, 1, 2 and 3, then we say that quality of the component is up to the mark. But if we found huge variation in the standard error in every shift, then we can say that, let's say for second shift the variation is huge, that standard value is deviated a lot from shift 1 and shift 2. Then we say that there is a problem in shift 2. So this is how you can utilize the value of standard error. So first sample, second sample and third sample. So are they behaving in the same direction or not? That a decision is made by the standard error. We can take a simple example. We have three divisions, TA, TB and TC. So the performance in AIML course in TA, TB and TC may not be same. So based on the standard deviation, mean and number of students in the class, we can calculate standard error. And based on that value of standard error, we can compare the performance of the student from each division. So that can be another example of standard error, where we can use standard error to compare the performance of the student. Then the extended version of standard error is coefficient of variation. It is defined as the percentage ratio of standard deviation to the arithmetic mean of the distribution. So this is again the just a percentage part is there. So here instead of the sample, here we are just dividing it by mu, that is mean, and multiplied by 100. So it will be in percentage. So these are the two parameters of dispersion, and that can be used to compare the samples performance of TA, TB, and TC in numerical and statistical course, for example. This is how we use measures. Again, when we talk about the popular shape of the frequency distribution, or when we say 6 sigma, then we see similar kind of symmetric distribution. And here the center line represents the mean, and in case of standard distribution or normal distribution, mean, mode, and median are at same point. And from that vertical line, both side 50% data is distributed. And theoretically, we are expecting normal distribution when we generate a lot of data. Now, suppose a machine is there, let's say A, and that machine manufactured a component and its distribution is like this. So this is mean, and this is, let's say, x1. Instead of x1 and x2, we will take some random values. Okay. Say here, let's say we will take 1, and here we will take 10. So this is the behavior of machine A. It manufactures the compound with like this distribution. And you are a design engineer, and you are expecting a different kind of distribution where there is some mean value and there is some upper limit and lower limit. Let's say 0.8, and here you are expecting, let's say, 11. So as per design, the lower limit is 0.8 and upper limit is 11. And this particular machine A manufactures the component with a lower limit 1 and upper limit 10. So 11, 10. So 11 is larger value compared with 10. So, and again at lower end, expected is 0.8, but machine manufactures up to 1. So here we can say that we can use this particular machine to manufacture that component because it tries to satisfy the design requirements, right? Because you are expecting a very wide range of data, but the accuracy of the machine is much better. Let's take another example. As per design requirement, your accuracy should be 1, lower limit, and maximum limit is 10. However, the machine manufacture 0.5 and 20, right? So when we compare the design requirement and the capability of the machine, then in this case we say that the machine is not good for manufacturing the components that satisfies the design requirement. So we should not use this machine to manufacture that component. Accordingly, we need to take decisions. Then we will go ahead for skewed distribution. So a distribution which is not symmetrical. Symmetrical means this is the standard condition. So if, and in most of the cases, it is very difficult to get a symmetric distribution because of the scarcity of the data, availability of the data. So other distributions are called as skewed distribution, and it may be positively skewed distribution or negatively skewed distribution. And if on right side the tail is very long, then it is called as positively skewed distribution. If there is a long tail on the left side, then it is called as negatively skewed distribution. And you can check the position of mean, mode and median in both the distributions. Okay, and when you get similar kind of distribution, then you should make some kind of conclusion. For example, suppose you give examination of numerical and statistical distribution, and there are around 80 students in our class, and if you plot a distribution, if you observe a distribution like this, then what we can see, many students received very good marks, right? So we can draw a conclusion that the examination is simple, or because of this online examination pattern, you try to get answer from the books or online platform and submitting, that's why you are performing better. Suppose in the same examination, if we observe positively skewed distribution, then what could be the conclusion? The question paper could be very tough. That could be the conclusion. Or the students in that particular class, their intelligence level is not up to the mark, or they are not performing good in the examination. So that kind of conclusion can be drawn. And suppose if you get a curve like this symmetric distribution, then what we conclude, that the question paper is balanced. Also, the performance of the distribution student is also measured accurately. Okay, now we will go ahead again. Skewed distribution. This is how we need to extract the feature of skewness, and based on that we need to make the decisions or predictions. Then next part is kurtosis. So kurtosis refers to a degree of flatness or pickedness in the region about the mode of a frequency distribution. So when you look at the three different curves, mean is exactly at the center. But when you look at the shape of the distribution, it is different. So this may be the outcome for T A, T B and T C classes, maybe, right? Based on your performance in the previous semester examination. So this particular distribution will help us the distribution of the data, especially around the mean, right? So the amount of flatness or pickedness is there. There are three different types, and that we already discussed in previous semester. Again, sometimes we need to rely on quartiles. So suppose in a class 100 students are there, and they ranked in descending order. So the rank one student at the top, and the student who received least mark, he will be at the bottom. So first means topper, and the 100 means the student who perform very worst. So the sample 25% is called as first quartile. So students who ranked between 1 to 25, they will be in quartile 1. Then the students who rank between 26 to 75 will be in quartile 2. And the remaining students 76 to 100 will be in quartile 3. So what we do, we rank the student or the data from in a descending order. Let's say topper will be at top, and the worst performer at the bottom, and we divide the data into different groups. So first 25 quartile 1, then second is 26 to 75, and last one is lies 76 to 100. And you can see here quartile 1 first 25 data, then second quartile and third quartile. So 0, 25, 50, 75 and 100, right? So the data is categorized accordingly, and this particular lane, that is the distance between Q1 and Q3, is called as interquartile range. And here interesting thing is that we are calling Q2 as a median, and generally it is the median of the data. Okay, then we will go ahead and we will talk about correlation. Again and again we are talking about these three curves, because when we talk about data and when we try to define the relationship between two variables, correlation is very important. In previous slides, whatever we discussed, we talked about a single data set. 100 students are there and what is their distribution. But here, generally we try to find out the relationship between two parameters. For example, age and blood pressure. So we may be interested to know, as age of a person increases, whether his blood pressure increases or not, or there is no relationship between age and blood pressure. So that could be a question. So we collect the data, age, given range and corresponding blood pressure. And if we found that all the collected data is spread like this, then we see that there is no relationship between age and blood pressure. If as age increases, blood pressure increases, then we say that there is a correlation, and it is positive correlation, because as one parameter increases, other parameter increases. And if as age increases, if blood pressure decreases, then we say that negative correlation is there, but it is negative correlation, because as one parameter increases, other parameter decreases. So if we collect the data of people related to age and their corresponding blood pressure, then you may get variety of curve, and that curve can be compared with these curves, and you will come to know what type of correlation is there. Again, age and probability of death. So you may be interested to know, as age increases, what happens to the probability of death. So you will collect the data and you will try to put on a graphical form, and you will compare that with this standard, and you will make a decision. Again, temperature and work efficiency. So here in each and every example, so there are 5 examples you can see. So in first example, age is one parameter and blood pressure is second parameter, and we are trying to find out what is the relationship between these two parameters. Again, temperature is one parameter, work efficiency is another parameter, and we are interested to know, is there any relationship or not. If there is any correlation, then what kind of correlation? And again, we have seen that if the correlation coefficient is close to 1, +1 or -1, we say that there is a stronger relationship between these variables. But if the value is close to 0, then we say that there is no correlation between these two variables. So in order to find out the relationship between more than two variables, then we came across correlation. And yesterday, while calculating principal component analysis, we talked about covariance. So ultimate objective of covariance is also same, to find out the correlation or to study the correlation between two variables, let's say x and y. And we saw the certain steps. We use this formula to find out correlation between xy, correlation between yx, correlation between xx, correlation between yy, and we prepared that matrix, right? Again, the extended version of the covariance is correlation coefficient, and we use this particular formula, covariance xy divided by sigma x and sigma y. It is standard deviation, and whatever answer will come, then if it is close to +1, we say strong correlation. If it is close to -1, strong correlation. If it is close to 0, no relation. If it is middle, let's say close to 0.5, then we say weak correlation. So this is about Carl-Pearson correlation coefficient to decide how strongly the data, different variables are related. Again, one more correlation coefficient estimating method is Spearman's rank correlation coefficient, and this is another formula for the same. And similar kind of interpretation is there based on the value of this row, and that we already discussed. So those who are interested to know more about the covariance Carl-Pearson, they can refer the videos of statistics method or refer the PPTs which we discussed previously, okay, in previous semester. So briefly we will see which different statistical features we saw. So related to central tendency, we saw mean, mode and median. Related to spread of the data about the mean, we saw range, variance and standard deviation. Again, in order to compare different samples and based on their dispersion, we saw standard error and coefficient of variation. So we can make a decision whether both the samples are taken from the same population or not. Then standard frequency distribution or popular shape of frequency distribution we saw. Again, we saw the skewness and how the interpretation is made using the skewed distribution. Then again we saw kurtosis. Even though the mean of all the samples are same, but the shape is different, and that flatness or pickedness decide the end result. Again, we saw the quartiles, and generally when we rank the students, just as we saw the example, we go for quartile. So generally we also say that if we get marks above 75, then we can call it as a distinction. Students is in distinction, and accordingly we can divide the remaining things. Then when we talk about more than one variable, let's say age and blood pressure, and if we are interested to find out the relationship between them, if there is any relationship, then how strong that relationship is there, correlation is there, then in that case we use the concept of correlation, and there we find out whether the relation is there or not. If there is a correlation, then it is whether it is positive correlation or negative correlation, that we check. And in order to quantify that value, in order to make a proper decision, we can use either covariance, Carl-Pearson correlation coefficient, or Spearman's rank correlation coefficient. So these are the some of the features that can be used to check what type of correlation is there between different parameters. So that's it from my side. If you have any question, you can unmute yourself and ask the question.